So we're going to start off our discussion of differentials by reminding you of something that you already know about linear functions and seeing how that fact still applies to planes. So here's our concrete scenario that we're going to use to understand this. We have a bicycle factory, and it costs you $500 a day just to make the payments on the equipment for that bicycle factory. And then each kid's bike you make costs you $20 for labor and materials. And we want to know, if you change the number of bikes that you make in a day, then how will your total cost change? So, well, let's see. We've got an equation here. Our total cost right now is our total cost is 20. Let's let x stand for the number of kids bikes we make, right? Plus so 20x plus this fixed cost of $500. So you can see, all right, since each bike costs $20 to make, if I change the number of kids bikes I make, then I just have to multiply that by 20, and that will tell me how much my costs change. All right, so this is always true for a line, right? If you take the slope times the change in input, then you get the change in output. All right, that's simple enough. Now, if for some reason my cost had been a nonlinear function instead of a linear function, similar principle would still apply. Let's say my cost was equal to x squared plus 500. Then the change in cost is going to be equal to the slope times the change in input. So we have delta c, change in cost, is the slope times the change in input. It's the same concept, right? In fact, if we were making about 10 bikes, then the slope would be, that would be dc dx, right? The rise over the run. That would be equal, the slope evaluated at 10 would be 2 times 10, which is a slope of 20. So if we make about 10 bikes, then if we make more or less than that, our costs are going to change by about 20 times the change in input. In this case, if it's a nonlinear function, we need to know where are we talking about, because the slope is different at different locations. So we have to plug in a value for that to actually get a linear approximation out of this problem, or to know exactly how much our thing will change. So we could say, though, that sort of in an infinitesimal sense, if you make a teensy tiny change in the input, then it gets multiplied by the slope to get the output, right? So the change in output is equal to the slope times the change in input. That's just a rearrangement of the usual slope equation, right? The slope is the rise over the run. That would be the change in output over the change in input of your problem. So a differential, we just have rearranged that. All right, so anyway, we get the sense that if you know the slope, then you can figure out from the change in input what the change in output would be. Let's take this up into a context where there's more than one variable in the problem, more than one independent variable. We've got our factory, but we've added a new line where not only do we make kids' bikes for $20 each, but we also make adult bikes, and they cost us $20 each. So how will our cost change if we change the inputs? Let's see. First, we know that the cost is equal to $20 times the number of kids' bikes we make, plus $30 times the number of adult bikes we make, plus our $500. So we could ask, well, what if I change the number of kid bikes or change the number of adult bikes? How will my costs change? And you can see that since it's linear, you could just take the slope times the change in the kid bikes plus the slope times the change in the adult bikes. Okay, so this just has a similar form, right? So as to before, it's just we have two possible inputs that we could change. We could actually write this as a matrix product. We have a matrix of slopes, right? So a 1 by 2 matrix of slopes times a vector, which is just a tall skinny matrix of changes in inputs. So we can kind of write it in a similar form. There's slopes, right, instead of just slope, times change in input. And it's the slope matrix times the vector of changes in inputs that gives you the change in output. Okay, so if perhaps your cost function was nonlinear, you could still do something similar. Let's say our cost function was x squared plus, I don't know, y cubed, right, plus something. Then we could still find, we still think about it this way: the change in output is going to be the slope in the x direction, which in this case is 2x, times the change in x. And the slope in the y direction, we can just compute a partial derivative, right? Pretend like x is constant and take the derivative with respect to y. We would get 3y squared delta y. So again, we could write our change in cost as a slope matrix, right? Or a matrix of partial derivatives times a vector of changes in inputs, or a tall skinny matrix of changes in inputs. So we can sort of break it out into that same idea that the change in output is going to be a slope matrix, so not a single slope but a set of slopes, times a change in input for our equation. Let's look at another scenario. Oh, actually, to use this, right, we would, to get actual values for our slopes, we'd have to know what x and y are, because on a nonlinear function the slopes are changing. So if you actually wanted to figure out your true change in cost, you'd have to know where are you, because that would specify what the slopes are at the particular location. Versus something linear, the slope is the same everywhere, and so the slope matrix doesn't depend on the variables. So back in your bicycle factory, let's assume that you add another product line. So you're going to have your costs now. You're still going to be making kids bikes. They cost $20 each. You're still going to make adult bikes. They cost $30 each. But now you're going to add, I should put a Y there. Now you're going to add tandem bikes that cost $50 each. So we can ask about if you change the number of any one of these inputs, like change the number of kids bikes, or change the number of adults bikes, or change the number of tandem bikes, then how will your cost change? So let's see, then delta c is going to be the slope in the x direction, right? Basically the partial derivative with respect to x times the change in x plus the slope in the y direction. That's the partial derivative with respect to y times the change in y plus the slope in the z direction times the change in z. So, okay, so we can see the change in our outputs is going to be this matrix of slopes, right, or a matrix of partial derivatives, times this matrix or vector of changes in input. So again, we have that same pattern, that the change in output is equal to the slope matrix, right, or derivative matrix, times the change in input. We can organize it in that way. Okay, so now let's add another wrinkle. Again, notice that the matrix here, I should say, this matrix is a 1 by 3 matrix, right? There's one row because there's one output, the cost, right? And there are 3 columns in this matrix, one column for each of the inputs. So we have a 1 by 3 matrix for this function. If this had been a nonlinear function, instead of having constants here for the derivatives, then you would have had functions that depended on the location, because on a nonlinear function then the slope is different depending on your location. But the same principle would apply. You could still write the change in outputs as some matrix of slopes. We'd call that, it's a matrix of partial derivatives, so put them all together in a single matrix, we'll call it the total derivative, times a matrix of changes in inputs, or a vector of changes in inputs. Alright, we're going to add one more wrinkle to this problem, and that's the shipping costs. So if you're going to ship things out, once you've made them, it's going to cost you $5 to ship a kid's bike to the wholesaler. It's going to cost you $7 for an adult bike, so 7 times the number of adult bikes you make. And it's going to cost you $10 to ship out a tandem bike. So now we have a function. This function has 2 outputs, actually. The first output is, so it's a combination of 2 functions, right? But we can think of it as the 2 outputs as being one piece, right? A vector of outputs. This first one is the production cost, right? And the other one is the shipping cost. So we want to look at then, how would production costs change? Well, that would be 20 delta x plus 30 delta y plus 50 delta z. And the change in shipping costs is going to be 5 times the change in the number of kids bikes you make, and 7 times the change in the number of adult bikes you make, and 10 times the change in the number of tangent bikes. So again, we can write it as we can write it in the form, in a matrix form here, as here's the change in our 2 outputs. Right, so there's our delta outputs is equal to a matrix of partial derivatives. So the partial derivatives we have are the derivative of the first with respect to x, the derivative of the first with respect to y, and the derivative of the first with respect to z. And then the second row of our total derivative matrix would be the partial with respect to x of the second component, the derivative of the second with respect to y, and the derivative of the second with respect to z, times our changes in x, y, and z. This time, if we think about it as a function that has 3 inputs and 2 outputs, then the total derivative matrix here is a 2 by 3 matrix. Now, if our function had been nonlinear, then this total derivative matrix would just depend on the values of x, y, and z, because on a nonlinear function the slope is different at different locations. So if our function had been nonlinear, then this would only be approximately true, right? So we could change this to approximately true in the case of a nonlinear matrix. But in all cases, we have basically the change in outputs is roughly the total derivative matrix times the matrix of changes in inputs, or the vector of changes in inputs.